everyone. This is lesson 1-4, extrema and average rates of change. Our learning target for today will be for students to be able to determine intervals on which functions are increasing, constant, or decreasing, as well as determine the maxima and minima of functions. This specific video will focus on determining the maxima and minima of functions. Before we begin talking about maxima and minima of functions, we need to have some key vocabulary or discuss some key vocabulary that will be part of our discussion. Critical points are points of a function in which a line drawn tangent, you should remember the word tangent from geometry, a line drawn tangent to the curve is horizontal or vertical. So to give you some examples of this, if I sketched a parabola, so the function y equals x squared, looks something like this. This function, y equals x squared, has a critical point at x equals 0. At x equals 0, I can draw a line that is horizontal through that point. This blue line is called the tangent line. The word tangent means to touch. And the tangent line is horizontal. Thus, this point right here, which I will often refer to as a minimum or a turning point, that point is considered a critical point. So the critical point is where a critical point on a function is where the tangent line can be drawn either horizontal or vertical. To give you another example where the tangent line could be drawn vertical is the function y equals x cubed. If I draw y equals x cubed, we have this point right here. And at that point, our tangent line could be drawn vertical. Okay, so this right here, this blue line is our tangent line, and it's drawn vertical. And so therefore, this point right here, tangent means to touch, which means that the tangent line can only touch the graph of the function at one point or in one spot. Therefore, the function has a critical point at x equals 0. So those are just some examples of critical points where the tangent line is either horizontal or vertical. If we move on to our next key vocab word, the word extrema or extreme discusses critical points at which a function changes its increasing or decreasing behavior. Okay, so a point where the function is switching from increasing to decreasing or from decreasing to increasing can be called an extrema. An extrema can also be referred to as turning points, which are labeled either as a maximum or minimum value. Now, there are some things called, there's two different types of maximum and minimums, or maxima and minima. We have something called relative. Okay, we can have a relative maximum or a relative minimum, or we can have something called absolute maxima or minima. So we could have a relative min or max, or we could have an absolute minimum or maximum. Okay, for instance, this point right up here on y equals x squared, that is what's called a relative minimum. It's a relative minimum because it's the lowest point on the graph. It's got the lowest y value on the graph. And our function here is moving from decreasing until I hit this minimum or low point, and then my function starts increasing. So to back up what we said about an extrema, it's a critical point at which a function changes its increasing or decreasing behavior. So this right here is called an absolute minimum. Here, this point is called an inflection point, which we're going to talk about right here in a minute. This point right here is called a critical point or a point of inflection, and the function is not switching from increasing to decreasing here. Rather, it is going to change its concavity, or the way it's bent. Right here our function's bent downward, and here our function is bent upward, or curves upward, and here this function is curving downward. The function, as I move from left to right, is always increasing because my y values keep going up and up and up and up. So this function is increasing from negative infinity to positive infinity. It never changes direction. It never switches from increasing to decreasing. So we cannot call that point right here, this point right here, we cannot call that a minimum or a minimum or maximum, because the graph is not changing direction. Rather, it's called a point of inflection. Now, to give you an example of an absolute max might look like this function right here, y equals negative x squared. If we have y equals negative x squared, that function has an absolute maximum because it's the highest point on the graph. This point right here, the function is switching from increasing, and then at this point the function begins decreasing. So this is called a turning point right here, or an extrema, which this is going to be an absolute maximum. Now, there's something called relative max and min, and if you think about a relative minimum and a relative maximum, something like this graph, this point right here would be called a relative min. This point right here would be considered a relative min. Relative max, because in relationship to the points around it, this is the highest point on the graph. However, it is not the highest point. It's not the highest point on the graph completely, because this arrow here is pointed upward towards positive infinity. So the highest y value, since the function is increasing infinitely here at the end, this function, or this point right here, is only considered a relative maximum rather than an absolute maximum. And in order to be an absolute maximum, it has to be the highest point on the entire graph, not just in that particular region. Okay, so right here, this function, we have a relative max, and down here, this is going to have a relative minimum right here. We have a relative minimum at this point because it's the lowest point on the graph in this region, not the lowest point on the entire graph, because the function is decreasing infinitely on the left end. So that's where the end behavior is tied in. The end behavior will help you determine whether a point is a relative max, an absolute max, or a relative min or an absolute minimum on the graph. So going back to a point of inflection is where the graph is changing shape, but does not, I repeat, does not change its increasing, decreasing behavior. It's not a turnaround point on the graph, but instead the curve changes from being bent upward to being bent downward, or vice versa. So like I said, y equals x cubed is a perfect example of this. The function is increasing from left to right infinitely. However, at this point right here, this piece of the graph is what's called concave down. It's bent downward, looks like a downwards parabola. And then here, the function is bent upward, or is considered concave up. And so at this point, our function is switching from concave down, frowny face, and at this point, it now switches to concave up. So when your graph is changing concavity, switching from concave up to concave down, or in other words, changing how it's being bent, that point is called a reflection point rather than an extrema. On this page, we're going to discuss relative and absolute extrema, and I kind of outlined some of this on the last slide, so I'm not going to go through all of this completely, but I am going to talk about the models here, the graphs that they give you. This point right here, if we have this function f of x, this point here would be considered a relative maximum. This is a relative maximum because compared to the points around it, it is the highest point compared to those around it. So we have a relative max at that function, whereas right here, this point right here would be considered a relative minimum. It is not the absolute lowest point on the graph because, again, my end behaviors are both pointed down. So since at the ends my graph is approaching negative infinity, there's no way that this has the lowest y coordinate on the graph. So we call it a relative minimum because it is the lowest point in that region of the graph. Now here, this point right here could be considered, or is considered, an absolute maximum. And we consider this point an absolute maximum because it is the absolute highest point or highest y value the function reaches on the entire graph. Because my end behaviors are pointed downward, we know that this is the peak or the top of our graph. There's no point that the graph reaches higher than this, so therefore this point right here is considered an absolute maximum. Whereas this point right here was a relative maximum because this was not the highest point on the graph. It's slightly lower than this point right here. So therefore, this could be considered a relative minimum, relative maximum. Whereas this point right here is an absolute maximum. If I move to the function down here, we have this point right here. And this point could be considered a relative minimum because it's the lowest point compared to those points around it. It's a turning point. However, there is a point lower than this point right down here, and we're going to call this point the absolute minimum because it's the absolute lowest point on the graph of the function. So we're going to call this a relative minimum, whereas this point right here is called the absolute minimum. And I know that this is the lowest point on my graph because if you look at the behavior of my ends of my function, this graph, this end, the left end is pointed up towards positive infinity, and this right end is also pointed up towards positive infinity. So to give you one more point though, this point right here is also a turning point, and that point could be discussed as a relative maximum because it's not the absolute highest point on the graph, again because my end behaviors are going to continue upward towards positive infinity. So we would call that point, that turning point, or change of direction, where the function is switching from increasing here to decreasing here. Over this interval, the function is decreasing, whereas the function is increasing here, so this would be a relative maximum. Okay, in example 2, we're going to estimate and identify extrema of a function, and we're going to estimate and classify the extrema to the nearest half a unit for the graph of f of x. And we're going to support our answers numerically, and how we do that is by providing a table of values. Okay, we're going to support our answer with a table of values. So I'm going to start by having you graph this function on your graphing calculator, and what I want you to do is then go to your table of values. And I'm going to go from an x value, let's start in my table at an x value of -4, all the way up to an x value of +4. So when I type into my table, after I've typed in my equation here into my equation editor, I'm going to go -4, -3, -2, -1, 0, and then I'm going to carry over here and say +1, +2, +3, +4. And I want to look at what happens in my table to support where I think I have a relative min, max, or absolute minimum and maximum. Because my end behavior here, my left end is pointed up towards positive infinity, and my right end is pointed towards negative infinity, we will not have an absolute extrema here. However, this point right here and this point right here, I need to determine as being a relative min or relative max. This point, since the graph, this point here is going to be a relative minimum because it's the lowest point on the graph compared to those points around it. So I'm going to say this is a relative minimum. And I'm going to write that down, relative min. And I'm going to say that this point up here is considered a relative maximum because it is the highest point compared to those around it, not the highest point on the graph. So I'm going to say it's a relative max here, and I'm going to support that answer by filling in my table. So filling in my table, I get 1268 when x equals -4, 279, 18, -7, 0, 3, 14, -27, and +4 is -372. Okay, so what I see here is a pattern that my function right here, my y values, as I move from 1268 to 1270 or 279 rather, to 18 to -7, back up to 0. So for these x values, right in here, for these x values, my function is decreasing because my y values are moving in the downward direction. My y values are getting smaller. And somewhere between -1 and 0, my function changes direction. Well, I guess I didn't really follow the instructions here because they wanted me to go by the nearest half a unit. So I should have included some values that were half a unit. So I should have gone like -4, -3.5, -3, -2.5, -2. And so if I go back in my table and do that, you can see that we know that our minimum occurs somewhere here between -1 and 0, which we also can see on our graph at this point. This point right here has an x value between -1 and 0. And if I make my if I go up by half a unit here at -0.5, I see that I'm at -2.719. And then after this point right here, after this point, my y values are increasing again. When I move from an x value of -2.719 to a y value, -2.719 to 0, that's an increase. So I know this point that I just circled right here, this point at -0.5, -2.719, that my function is at a minimum. Because the graph at this point right here, my graph switches from decreasing, and then my y value starts increasing again. So this point right here is where the graph changes direction. This is the last point where my function's decreasing, and right directly after that, my function starts increasing. Now, you can see that here, I move from 0 to 3 to 14. All of a sudden, I bump back down to a -27. So I'm going to go in my table and plug in 2.5. And at 2.5, I'm at 9.8438. And so we can see that at an x value of 2, right, the highest point, the highest y value we get is at 14, and then my function starts decreasing again. We move from 14 to 9.8 to negative 27 to negative 372, and by our end behavior, because the graph is pointed downward, the graph will never increase again. And so this point right here is a relative maximum, because this, again, is the highest y-coordinate we ever reach. So what we want to do is estimate and classify the extrema. We've already classified them as being a relative min and a relative max. And my relative max occurs at 14, and my relative minimum occurs at negative 2.719. Now, we can be more clear about what our relative max and min are. We can give the ordered pairs, which I've circled in my table. I'm going to say we have a relative min at approximately negative 0.5, comma, negative 2.719. And our relative max, this is a relative max right here, occurs at 2, 14. Now, what we have here is just a relative min and max. We have no other extrema. We have no absolute extrema because our end behaviors are pointed in opposite directions. So the absolute y value would be positive infinity, and the absolute y value would be negative infinity, because our range is from negative infinity to positive infinity. Okay, in this check for understanding, we're asked to estimate and classify the extrema to the nearest half a unit. Do not do what I did in the last example and count by ones in your table. Rather, count by halves. Just based on what this graph, if I look at the width of our graph, you could probably go from negative 2 to positive 2 in your table, counting by halves, because all the minima and maxima, or in other words, the extrema, occur in between x equals negative 2 and x equals positive 2. And you want to support your answers numerically with a table. Okay, so provide a table to support your answer. You have 4 choices, A, B, C, and D. And so what I want you to do is graph this function, provide a table, and then figure out where your extrema are for this function. When you are finished, submit your answer, and you are complete.